Okay, it's a real pleasure to be here. And thanks, Charlie, for that wonderful introduction to topological superconductivity. In fact, a lot of what Charlie spoke about in his talk, at least some of it, I hope to show you experimentally in this talk. So what I'd like to talk about today is signatures of dispersing Majoranas, meaning 1D helical Majorana modes that can be realized in ion-based superconductors. So I'm giving two lectures. This one is about topological superconductivity, and tomorrow's lecture is about topological crystalline insulators. And so I'll introduce STM today a little bit, and then I'll talk more about detailed STM techniques like quasi-particle interference and Landau level spectroscopy tomorrow. So today, everything that I'm going to do using STM is simple spectroscopy, so I'll introduce that, and I'll leave the rest for tomorrow. Okay, so since this work is pretty focused, let me just tell you who did a lot of the work. The work on ion-based superconductors was done by this group of people, primarily Zhenyu Wang, and we had theory help from Taylor Hughes and Dirk Moore, and our single crystals were from Genda Gu's group. Okay, so we've been talking about Majoranas for the last hour or so, so it requires no introduction. Essentially, it's a particle that is its own antiparticle. And Majoranas were hypothesized in terms of elementary particles, but as we all know, there are no elementary particles that have been conclusively shown to be Majorana fermions, right? And the only possible candidate, as far as we know, is the neutrino. And in fact, let me just show you an example of an experiment that's being set up to figure this out. And these are giant experiments, and you can see from this description, it's got all this germanium, it's deep underground, and in fact, this thing called a Majorana demonstrator, it's only the first step to actually showing whether or not the neutrinos might be Majoranas. Once this thing works, they'll have to build another one that's much bigger to actually prove whether neutrinos are Majoranas. So these are very complicated experiments. However, in condensed matter physics, we hope we can realize these kinds of Majorana modes much more easily in the lab. So why are we interested? As Charlie Kane said, we are interested for a number of reasons. These are fundamentally interesting particles. They're non-abelian. And of course, the other thing is they might be useful in quantum computation, right? And the only reason I put this here is to show you that there are ways to actually braid these particles and use these braiding schemes to implement all kinds of computations that might be useful for a quantum computer. The key here is that these things are far separated, so they're very, very insensitive to dephasing effects. And that's what makes them so attractive. So I hope that by the end of the lecture today, you'll be able to answer the question, how do you create a Majorana fermion in a solid? That's my goal for today. So let me just start with asking, what do you need, right? What you need is a particle that is its own antiparticle. So this is what you need. So this means that the first requirement is that the state at energy E and the state at energy minus E must be identical, right? And we know that the best way to get a material where these two states are the same is in a superconductor. So let's just directly go to a superconductor, right? The excitations of a superconductor are Bogoliubov quasiparticles. These are superpositions of electrons and holes. And let's just look at the creation operator for one of these quasiparticles. It looks like this. This is the creation and annihilation operator. Now let's ask the question, what happens if we set the creation operator equal to the annihilation operator? And let's just look at a superconductor and say, what do we need in order to make these two equal? Okay? So if you do this, if you set these two to be equal, then this needs to be equal to this. And let's just compare the left-hand side with the right-hand side. What you'll find, let's just look at these two creation operators. The first thing you need is the UK should be equal to the VK. That's not hard to do in a superconductor, right? That means that the particle and the number of particles and holes that make up these Bogoliubov quasiparticles should be sort of similar. You can do that. But another thing you do need is that this creation operator has a spin down, and this creation operator has a spin up. So this means that in a normal superconductor, there is no way you can get this equal to this. And the only way to do that is to somehow eliminate spin as a separate quantum number. Okay? So that's why you need spinless superconductors, like p-wave superconductors. So the question is, how do you eliminate spin as a separate quantum number? So let me just show you a few ways. One is you can use a triplet p-wave superconductor. So if you have a spin triplet superconductor, the pairs are composed of the same spin particles, two spin ups. And once you have that, you don't have to worry about spin anymore. Okay? So that's one way to get rid of spin. The problem with this is that there are very few known spin triplet superconductors. It's not only important for the superconductor to be in a triplet state. It also has to be in a chiral pairing state in order to get these Majorana edge modes. So this is a tall demand, and the only compound we know which has a sufficiently high TC is strontium ruthenate, and that also is in question now. One thing I have to tell you is that recently we've discovered a new superconductor. This was discovered in Maryland, uranium tellurium 2. I don't think I'll have time to get to it today. But if I do, I'll show you a little bit data on that superconductor. This is a new superconductor that actually might also be a chiral spin triplet superconductor. In any case, these are really hard, so let's think of other ways. Another possibility is, like Charlie said, you can use something with strong spin-orbit coupling. So let's consider this possibility. Let's take a semiconductor with strong spin-orbit coupling, right? And in this semiconductor, you would have these Rashba split states due to the strong spin-orbit coupling. That's these dotted lines. Now let's turn on either a magnetic field or couple this to a magnet somehow. If you do that, you can create a gap here, right? And then if you can tune the position of the Fermi energy such that the chemical potential lies inside this gap, you've achieved your objective. Basically, you've gotten rid of one of these branches, and you're left with simply one branch, one dispersing branch, right? And the important thing here is that because of strong spin-orbit coupling, the spin is tied to the momentum. So at every momentum, the spin is well-defined. And once you have such a situation, because of spin momentum blocking, spin is no longer essential to describe the system, right? Because once you know the momentum, you know the spin, and that's how you get rid of spin in such a system. Okay? So this is pretty complicated and difficult to do, and as Charlie showed you, there have been quite a few experiments, but a lot of stuff using this geometry, except Liazani's group, I think, and a couple of other STM groups, a lot of the work is being done by transport. So the third possibility is to use topological insulators. And as we know that on the surface of a 3D topological insulator, because you have vacuum, which is topologically trivial, it has an even Z2, you're bound to have these interesting surface states. And these surface states have exactly the kind of structure you need in order to get a topological, at least topologically non-trivial superconductivity. So let me just tell you why these surface states are interesting. So you can have like the surface of a metal like copper. Copper 111 has surface states. Those surface states have parabolic dispersion. And at any given energy, you have two electrons, one with spin up and one with spin down, right? Just trivial surface states. Now, if you crank up spin-orbit coupling, like on the surface of gold, you'll get Rashba split surface states, right? But the problem here is, again, at any given energy, you still continue to have 2 electrons spin up and spin down. And you can gap this out with magnetism or something like that, but the challenge remains that you have to move the Fermi energy into that gap and so on. However, in topological insulators, you get this, this kind of singly degenerate states for free, right? So the surface state on a topological superconductor has Dirac dispersion and spin momentum blocking. And here, at any given energy, you have only 1 electron with a well-defined momentum. So one hopes to use topological insulators to realize Majorana modes. So Charlie Kane and Liang Fu wrote a paper in 2008 where they suggested that if you took a topological insulator and proximatized it with an S-wave superconductor, then you might be able to realize Majorana modes in 2 geometries. In the first situation, what you would do is you would turn on a magnetic field, and you would see inside the vortex cores, you would see 0 bias bound states. And the second possibility is that if you could have 2 superconductors with a pi phase shift between them, then at the boundary between those 2 superconductors, you could get helical, linearly dispersing Majorana modes, so Majorana edge states. So these are the 2 possibilities. So this has been hard to do from an STM perspective. However, recently, there's been this new, this is not a new superconductor, but it's a new discovery that this superconductor, iron, selenium, tellurium, with approximately this composition, although you can deviate a little bit, could have non-trivial surface states due to band inversion on one of the bands. Okay? So there are multiple bands crossing the Fermi energy, but one of the bands is band inverted, and due to band inversion, there might be non-trivial, topologically non-trivial surface states in this material. So this is a pretty cool system because the TC of the superconductor is about 14 Kelvin. So you have a pretty high TC superconductor. Moreover, this is really important, this is an S-wave superconductor. It's actually possibly S plus minus, but still it's an S-wave superconductor. So this is what you need. So you have topologically non-trivial surface states potentially proximatized with an S-wave superconductor. So perhaps you could realize Majorana modes in this system. So the questions that I'm going to try to answer today are, can you show evidence for these non-trivial surface states? And can we see signatures of Majorana modes in this compound? So here's the phase diagram. The only reason I show you this is to show you that FETE is actually not a superconductor. It's a spin density wave material. FESE is a superconductor. So actually, superconductivity survives quite a bit when you put tellurium into iron selenium. And it's somewhere around this that band inversion is expected to happen, right? Right in the middle of this phase diagram. So it's not band inverted on this end, but as you put in more tellurium, the bands are expected to invert and give you this topological surface state. So this is the crystal structure of this compound. You can see it's a layered material. One interesting thing is, so these purple balls are iron. And one interesting thing is that if you look at it, you have selenium here, which is on top, and then you have these seleniums that are on the bottom. So when the crystal makes a choice, whether these seleniums are going to be on the top or the bottom, and in fact, you'll see this is really important because this provides an opportunity to get crystalline domain walls where the selenium switches from the top to the bottom, right? You can imagine these kinds of defects occurring naturally as the crystal is grown. This is the band structure of this compound. This is the Fermi surface. You can see there are 1, 2, 3 Fermi surfaces. So these 3 distinct Fermi surfaces, each of them gets gapped out by superconductivity, and you in fact have 3 distinct gaps. Now, what about the surface state? So it's these 2 bands, the band labeled PZ and this band here. These are the ones that are supposed to, as you add more tellurium, basically this band gap is supposed to close and reopen, and when it reopens, you're expected to see a surface state right here in this gap. And in fact, initial ARPAS studies, like just last year actually, showed that there might actually indeed be a surface state. So here's data, this is ARPAS data. This band here is this band, and you can see a Dirac-like dispersion that lives right here in this gap. Okay, so this is possibly the Dirac surface state. So the first question we wanted to ask, so when these results first came out, we were very curious because there was a lot of controversy about this material. Is it topologically non-trivial? Do we really have surface states? So the first question we were trying to answer is there any evidence for these non-trivial surface states in STM? Now, I'll show you tomorrow, you can often use more complex techniques like quasi-particle interference and Landau level spectroscopy to look at non-trivial surface states. But QPI can't be used for Dirac surface states near the Dirac cone because backscattering is forbidden. Okay, so that makes it really difficult. Also, Landau level spectroscopy is really, really hard in this material because there are a lot of other bands and the density of states is actually pretty high at the Fermi energy, right? So how do we tell if you have non-trivial surface states? One thing we can do is count the gaps. So let me just show you the data. Before that, let me show you how STM works. So it's a very simple technique. I think most of you must be familiar with it. You have a very sharp tip that you bring close to the surface of the sample that you want to look at, and you turn on a potential difference between the tip and the sample, and electrons tunnel across this vacuum barrier from the tip to the sample or vice versa. And this is exactly what we measure. We measure this tunnel current, and we can measure the tunnel current as a function of bias voltage, as a function of position, and as a function of magnetic field and so on, but our only measurement is actually the tunnel current. So usually all our experiments are done in UHV at low temperatures. For example, the measurements I'm going to show you were done at 300 millikelvin. And this is a quick slide to get a sort of intuitive feel for what the STM measures. So think about what you have. You have this tip, which is a filled Fermi C. That's what this is showing here. And you have the sample here. And when you bring these two together, initially the Fermi levels of the tip and the sample will line up, right? Now let's say you apply a potential difference between the two. You can raise, let's say, the sample Fermi energy with respect to the tips. And as soon as you do that, electrons can tunnel from the filled states of the sample to the empty states of the tip. And that's the tunnel current that we measure. And you can immediately see, even pictorially, that the number of tunneling electrons must be proportional to the integrated density of states of both the sample and the tip from the Fermi energy, right, to whatever the bias voltage, from the Fermi energy to the bias voltage. That's it. So the tunnel current is proportional to the integrated density of states from the Fermi energy, which we call 0 always, to the bias voltage. But the one important thing in STM that you have to realize, which will be important for my lecture tomorrow, is that in STM, we just don't measure the number of states from here to here. Each state is weighted by the square of the wave function, okay? And this is going to be really important when we do quasi-particle interference. So because the STM is sensitive to the square of the wave function, the wave functions die exponentially into space. So the distance between the tip and the sample basically controls the tunnel current. And because of that, we're able to do take very high resolution, atomic resolution images, because the tunnel current actually depends sensitively between the distance, on the distance between the tip and the sample. The other thing we do is spectroscopy. So what do we measure? We basically measure the differential conductance, which is dI/dV. And you can see from here that dI/dV is immediately proportional to the local density of states. We say local density of states, it doesn't only mean the density of states underneath the STM tip. It also means that each state is weighted by the square of the wave function. So you have to keep both of those in mind. So when I show you spectroscopy, I'm going to show you dI/dV as a function of bias voltage. 0 volts is the Fermi energy, and we can measure the density of states as a function of energy using STM simply by measuring dI/dV, right? And so, for example, if you were to measure the dI/dV for a metal, the density of states is featureless across the Fermi energy, so this would be 0. You would just get a flat dI/dV. If you were to measure dI/dV for a superconductor, you would see a superconducting gap with coherence peaks that are symmetric on either side of the Fermi energy. So this is, for example, the density of states measured on a topological crystalline insulator. This is not a superconductor. How do you know this? It seems to have a gap, but look, 0 is here. If it were a superconductor, this gap would be centered at 0. Okay, so this is not a superconductor. And here's the topography on this material. And one thing I want to show you is we often take things that are called dI/dV maps. So let's say this is a spectrum at some point here on the sample. What we'd like to do is we'd like to go to some particular energy, in this case, let's say 15 millivolts, and plot the height, that is the density of states as a function of position on this surface. So this is an example of a spatial conductance map at 15 millivolts on the same area, okay? And these spatial conductance maps can have a huge amount of information on how the density of states at a particular energy is varying with position. So we have a bunch of, this is what STMs look like, especially ultra-high vacuum STMs. You have these vacuum chambers, and you can't see it very well here, but underneath the table is a dewar, and inside the dewar is the STM, okay? All right, so now let's talk about ion-based superconductors. So here again is the crystal structure. The unit cell is doubled because you have the selenium on top and bottom. Now, let's do some STM. So we started doing this work actually quite a while ago. And the first samples we got, the only reason I want to show you this is you can see how important sample quality is. So the first samples we got, there were a lot of ion impurities. Each of these little dots is an excess ion, okay? And this is an S-wave superconductor, so this excess ion actually really destroys superconductivity. And in fact, you can anneal these samples in oxygen and get rid of this excess ion, but it actually it creates a lot of defects and impurities. So here's the superconducting gap. Here's 0. You can see it doesn't reach 0 on the sample with excess ion. And if you anneal it in oxygen, you can get rid of some of the excess ion, and still at 300 millikelvin, the gap still doesn't go to 0, okay? So then our experiments had to wait until we got these beautiful samples from Gendagu. And now this is a giant, for us, giant field of view, right? It's just about 100 nanometers. And if you squint, you can see the atoms. In fact, I'll show you a zoom in. But in this entire field of view, I think there are maybe there's one excess ion here, but maybe none. Okay, so if you zoom in, you can see the atoms. Now, all the contrast here comes from the fact that you have selenium and tellurium. In fact, you can count how many seleniums and telluriums you have. One of them shows up as a bright dot, and the other shows up as a dark dot. Okay, now if you were to take a line cut across this material and measure a spectrum at each point, so here I'm showing you spectroscopy measured from this point to this point, right? And so you can see here's a beautiful superconducting gap. The bottom here goes to 0. It's absolutely flat, and it goes to 0, okay? One interesting thing you see from this line cut is the gap varies quite a bit as from position to position. The other interesting thing is there are multiple gaps. There's not just one gap. For example, you can see the spectrum here. It has one bump, another bump, and a third bump. So there are 3 gaps in each spectrum. And in fact, this only, if you look closely, around 5 millivolts, there's actually another gap. So there are 4 gaps in each spectrum. So how do you characterize the superconductor? Well, we've been working on superconductors for a long time, so we know what to do. What we would do, yes?
What do you actually call a gap?
Ah, that's a really good question. So for us, anything that has a coherence peak is a gap. There are 2 criteria. One is that it should have, there should be something that looks like a peak. And the second, which is really, really important, is that it should be particle hole symmetric. So if you see the same feature on both sides of the Fermi energy, then you can define it as a gap. Now, there are certain circumstances where, phonons also look particle hole symmetric, but in this case, you'll see from the data that everything that we pick up is actually a superconducting gap. Okay, so let's ask what does, yes?
If you go next to the iron, do you see Shiva state?
Yeah, I'll show you. We have data on that. It's beautiful. There's a sharp resonance right at 0.
Does the Shiva state look different to what you have here in the state of the topological circuit or not?
That's a really good question. I don't have an answer to that.
I mean, it should.
Yeah, no, I don't, because we never studied the non-topological FESET. However, we've been growing films, and so I could take a look. Yeah, that's a really good question. Okay, so let's see what ARPAS says about these gaps. There's a lot of data from specific heat, optical conductivity, and since there are multiple bands, you have to ask what's the gap on each band. So just as a summary, let's just look at the ARPAS data. You have these 3 bulk bands out. They're labeled cleverly alpha, beta, and gamma. The gaps are 1.5, 2.5, and 4.2. Okay? Of course, if you have a surface state, then you should have a gap on the surface state. And in fact, Hongding has measured such a gap, and the claim is that that gap is 1.8 millivolts. Okay? So essentially, if you include that, the surface state gap, leaving aside the 4.2 MeV gap, below 3 millivolts, you should seek 3 gaps, 1.5, 1.8, and 2.5 millivolts. All right? So let's see what STM sees. I mean, of course, it's extremely inhomogeneous, but we have a huge advantage because we have statistics on the gaps. We can actually, in this field of view, we could take 200 times 200 points and measure the gap at every point. So if we have huge statistics, so I can show you what that looks like. This is what is called a gap map. This is not a conventional gap map. All I've plotted here are regions of 1 gap, 2 gaps, and 3 gaps. So let's just focus on this area for a second, and I'm going to show you a line cut across here just to see what it looks like. So here, the blue region has what we would call 1 gap, which is what is picked up by a computer program, right? And the green region has 3 gaps. And so you can see here, you start here with maybe 1, or we don't really pick up the shoulder. You immediately go into this region with 3 gaps, 1 coherence peak, 2 coherence peaks, 3, this is the 3rd coherence peak. And then eventually you end up in a region with 2 gaps here. You might ask, how can the same sample have different numbers of gaps? What's really happening here is that the gap magnitudes on each of the bands is changing as a function of position. And once in a while, like right here, the different band gap magnitudes merge together. And so you can't see them as separate entities. Okay, so that's what we see. And now you can go to all the 3 gap regions, and this is what the gap histogram looks like. Like I said, this is, hundreds of thousands of spectra. And then you can, from here, just fit 3 Gaussians to this. And from that, you can extract the mean gap values. And these are the numbers we get. And the fact that we have 3 gaps, 1.3, 1.8, and 2.4, already tells you that you must we probably have a surface state in this system, right? Because ARPES, the largest gap is 4 millivolts, which I'm not talking about because it's very fuzzy, right? So from ARPES data, they claim that the 1.8 millivolt gap is from the surface states, and that's exactly what we see. All right, so let's just see what happens now. We have a system that seems to have a non-trivial surface state. Yes?
So how did they define the gap?
They did low temperature ARPES, and they could see 1.8 is not so bad. Yeah. The thing about ARPES is that even though the peaks get broadened, the position of the peak, you can still catch the position of the peak.
Okay, but you still only see the occupied peak.
Oh, yeah, absolutely. They can't. So sometimes if they raise the temperature, they can see both sides. So they only see one side, and then they symmetrize it and assume that it's symmetric. So, but we can see both, so yeah, absolutely.
And in this map where you plotted the distribution of how many gaps you have, it seemed like it was not perfectly coming to the whole symmetric, the distribution of if you have 2 gaps, 3 gaps, and so on. In some spectra, the bubble in the whole was.
So in all, we only picked up peaks that were particle hole symmetric. We didn't, so the program was written to only pick up those peaks. Yeah.
Okay.
Yeah. So here is an impurity bound state. So here is an excess ion, right? And interestingly, if you go on top of it, you get this beautiful zero bias peak, okay? And this already tells you that there's something very interesting happening in this compound, right? The peak is really centered at 0. But then let's look at vortices. So like Charlie told us in the last hour, if this is indeed an S-wave superconductor with a topologically non-trivial surface state, if you turn on a magnetic field, then in the vortex core, you should see Majorana bound states, okay? So let me just try and motivate that a little bit. So all I want to show you is that if you take such a material, which is a proximatized topological insulator, then you can massage the Hamiltonian to sort of make it look like a spinless p-wave superconductor. That's all I want to show you. And we know that for a p-wave superconductor, the vortex cores have zero bias states. So let me just show you that really quickly. So if you have Dirac dispersions, the Hamiltonian can be written like this. So this is just linearly dispersing surface states. Now, if you proximatize this with a superconductor, you can describe the Hamiltonian the Hamiltonian that describes that system. It can be written down as simply this Hamiltonian plus the pairing term, which is this one. So if you do that, then the resultant Hamiltonian looks like this, right? And this is the superconducting gap. And this is something really clever. This was done by Charlie Kane and Liang Fu. You can define a new operator this way. And using this new operator, if you transform this Hamiltonian, then the projected Hamiltonian looks like this. And if you look at this Hamiltonian carefully, it looks exactly like a Hamiltonian for a spinless p-wave superconductor. So this just shows you that a topological insulator proximatized with an S-wave superconductor can be massaged to look like a spinless p-wave superconductor. And therefore, when you turn on a magnetic field, you can see, at least in theory, Majorana bound states in the vortex cores. So the one important thing here is, where is this? Yeah. This is an important number to remember. So delta squared over EF tells you if you have trivial Caroly-Metricon-de Gennes states inside the superconducting gap, this would be the energy where the first one would appear. So for this system, for the surface states, you can calculate delta squared over EF, and it is about 0.75 MeV. So 750 microvolts is where the first not trivial bound state should appear inside the gap. So there should be nothing really at 0. So if you have the resolution to distinguish between 0 and 750 microvolts, you should be able to see whether the system has Majorana bound states. So this is what, actually let me show you this one. This is what a DI-DV map looks like actually at 0 energy, right, where you should see these Majorana bound states. Each of these bright dots is the vortex core, right? This was done at 3 Tesla. And if you take a line cut across one of them, what you see is a sharp peak at 0. And I'm not going to dwell on this mainly because this work was done by Hong Ding already, right? The thing I showed you was our data, but this is published data by Hong Ding and his collaborators. And you can see that they found vortices where they could see these sharp modes at 0 energy. However, in their work, only 30% of the vortices showed 0 bias states, so there was still a question about what's going on in this system. Hanaguri has done more recent work on the same material, where he shows that at very low temperatures, if you can decrease the magnetic field, you can get up to 80% of the vortices showing bound states very close to 0, which are within resolution. His resolution at 100 millikelvin is pretty good, within resolution at 0 bias. So this does seem like a pretty interesting system. Okay, so what we were interested in was to actually ask, if you can see this, perhaps you can see this as well. Can we see one-dimensional chiral dispersing helical states in this material? So the question, so basically, Fu and Kane showed that if you have a pi phase shift, you can get dispersing Majorana modes inside the superconducting gap. Here, there are 2 important things. One is if you have a pi phase shift, you get this kind of gapless dispersing modes. But remember, these are topological. So one of the most important proofs of that this is actually topologically non-trivial is that they should bridge the superconducting gap, right? They should go from here to here. So that's really important. All right. So you need superconductivity, and you need something that's topologically non-trivial, and you need a pi phase shift. We have these 2. How do we get a pi phase shift? Okay. Now you can do it using, making devices, but that's really difficult. However, there is something that's pretty cool about this compound, and that is that, like I told you before, the crystal structure has this ambiguity. So these are the top seleniums, these are the bottom seleniums. These might have been the bottom, these might have been the top. There is this ambiguity. So when the crystal grows, once in a while, it can flip the top to the bottom. And when that happens, you'll get a domain wall, right? And actually, there's a paper by Jianping Hu, in fact, multiple papers, that showed that if you consider all the symmetries of this problem and include next nearest neighbor hopping, then if you have such a domain wall, then the superconducting order parameter can actually have a sign change right at such a boundary. Okay? So that's what we're looking for. So here's our beautiful sample, FESCT, no domain walls in sight, right? So if you I don't know how many of you have done STM. The beauty of STM is you can walk around and try to find things. So we did that. And if you go to another area, you can find areas with lots of domain walls like this, right? And in fact, sometimes you have to select samples with domain walls. So let's say you can do that and find domain walls. So here's one domain wall, right? It's this dark line here. However, if you take spectra along this line, you see nothing. You just see a superconducting gap. Now the question is, what do you expect to see? I'll tell you in a second. However, this is not the right kind of domain wall. The reason we know that is the kind of domain wall we're looking for should show pi phase shift in the crystal structure from here to here. If you do a Fourier transform of this, these are the Fourier transform peaks. You can see it's a single dot, and anything with a pi phase shift should show split peaks. Okay? So here's another domain wall, and in fact, I'll tell you, this is the right kind of domain wall that we're looking for. If you do a Fourier transform, you can see, if you zoom in here, you can see the split peaks in the Fourier transform. That tells you that there's some kind of a phase shift between this side and this side in the atomic lattice. Okay, this is just the atomic lattice.
The second, the one wall, you mean crystal structure?
Crystal structure.
Okay, not magnetic.
No, crystal structure. There's no magnetism in this compound. Yeah. Even though the N member has. Yeah. So you know, this is very crude. We can draw lines. These are just the atoms on one side. These are the atoms on the other side. However, we can do more sophisticated analysis and simply pick up the phase using Fourier methods. And so you can actually track the phase of the crystal structure and track it from this side to this side. And these red and blue shaded colors means that there's a pi phase shift, meaning the crystal structure has shifted by half a unit cell. Now, if you go to this domain wall, this is what you see. So far away, you see this superconducting gap. This is 0, so this is very much at 0. On top of the domain wall, you see this. So this is really already extremely interesting because, you know, I've done many different kinds of impurities in superconductors, and usually you see peaks, right? So there are two kinds of things you see. Either you see peaks inside the gap, or you see the gap itself shrinking, getting smaller or bigger. This is the first time we'd seen this kind of flat density of states, okay? So this is already, this is a line cut across this domain wall. This is sort of squished, I'm sorry about that. But you can see the superconducting gap, and you can see as you go across the domain wall, it's actually the same data. You see a flat density of states. Here, this is a color plot of the same thing. If you go across the superconductor, you see the superconducting gap. Density of states is suppressed. And as you go along the domain wall, you see a sort of featureless density of states inside the superconducting gap. Now, just to contrast this with another one-dimensional feature, we often see step edges in these systems. If you were to take spectra across a step edge, so here far away you see the nice superconducting gap. Right at the step edge, what you see is a bunch of peaks inside the superconducting gap, right? So you can see all these peaks. This is right at this edge. And this is another line cut. Again, you see a bunch of peaks. So this is very common in these kinds of superconductors. Okay. So the question is, where is this coming from? And this is sort of, I have another 10 minutes, I think. Yeah, okay. So actually, Charlie already alluded to this a couple of times, and he showed you can get one-dimensional bound states in a topological insulator. So I just want to motivate how you can get similar Majorana modes in this kind of proximatized system. So let's just start with a topological insulator, which has surface states with Dirac dispersion. Let's say this is like a Z2 topological insulator with time reversal symmetry. If you break time reversal symmetry, then you add a mass term to the Hamiltonian, and then the surface states obviously will get gapped out, and they'll start looking like this. Now, the dispersion of this massive Dirac system just looks like this, okay? Now, let's just think of a situation. If you could doctor a system where you could have a negative mass on one side and a positive mass on the other, meaning that this mass depends on position, right? Then let's ask the question, what happens at the boundary between these two areas? And you can actually, this is a very cute system to solve. You can sit down and write down the Hamiltonian and solve this Hamiltonian. So you take this Hamiltonian, and just for a second, you can set Py to 0, right? When you set Py to 0, the Hamiltonian looks like this, right? It has only this kinetic energy term and the mass term. And this is the 2x2 matrix that represents that Hamiltonian. And for this 2x2 matrix, you can guess a solution of this form. So this is the solution to the Hamiltonian, right? In our case, the mass is like it's got a step function. It's got, it's negative on one side and positive on the other. But in the most general case, the mass would be a position of x. And then you can take this gas and you can put it back into the Schrodinger equation. And then you get a sort of a very simple matrix that looks like this. And you can show, it can be shown, that you can find a solution for this when the energy is 0, right? And so for this 0 energy, you can find this is your solution. Okay? And now remember, we set py to 0. And if you put py back, py just gives you plane waves going along the y direction. So basically what this looks like is a bound state in the x direction with linearly dispersing, a linearly dispersing mode going in the y direction. Okay, so this is just for a topological insulator where you have a plus mass on one side and a minus mass on the other side. Now, let's consider a superconductor. We've already seen the BDG Hamiltonian. That's what it looks like. You have the Hamiltonian for the surface states, which looks like this, and then you have the term that gives you a gap. If in a superconductor you could have a gap of delta on one side and a gap of minus delta on the other, and you wrote down the Hamiltonian, it would pretty much look like the Hamiltonian I just showed you earlier. It would pretty much look like this, with the deltas substituting for the mass terms. So you can imagine that in a superconductor, you would get, right at the boundary, you would get these two chiral Majorana modes right at the boundary, because everything's doubled in a superconductor. Okay? So in fact, there are many ways of getting chiral modes. You can have these chiral modes when you have a sign change in the mass. You can get helical Majorana fermions where you have a sign change in the superconducting order parameter, and you can get chiral Majorana fermions if you have some way of getting a mass like a magnet or putting magnetic impurities and a superconductor. So you can have many kinds of edge modes. So we believe that we are in this situation where the gap has a sign change between the two sides. So if that's the case, then what you would expect right at the boundary is this linearly dispersing state. And if you ask yourself, in one dimension, what's the density of states of something that disperses linearly? It's flat. Okay? And so in fact, that's what we believe we're seeing. We're seeing that a linearly dispersing mode that goes right along this domain wall. You have a question?
First of all, I didn't fully understand the reasoning behind the fact that you're changing half that.
Yeah.
The phase shift
Yeah.
in the future.
Yeah.
That's first one. Second of all, do you have data in magnetic field? Like you see the gap?
Ah.
I assume these are 10 samples again. Like I put one helical edge node, there's two directions of the magnetic field and the gap.
I need $100,000 to buy a magnet which can apply a field.
Otherwise it can be 100.
Yes. Okay. You're absolutely. Yes. And so yes, absolutely right. We should, the next experiment to do is to put on a magnetic field in plane and see if we can see anything. We're going to do it. Yeah.
And the third thing that we actually done for your theory fabric is an actual calculation that initially basically with some proximity that takes into account where, like for example, I don't know where the surface state, which orbital it sits on. Like does it sit on iron mostly and
I would say the answer is no. There's no ab initio calculation right now for taking into account the orbitals of the surface state and showing what happens if you have proximity effect. Yeah. But your first question, I think I'll address that after I finish this last bit. Okay, so the last thing I want to show you, actually, I'm almost out of time, is one of the important things to show, if this is topologically non-trivial, is that this state must actually span the superconducting gap, right? So in fact, let me show you that. So right at 0 energy, this is a dI/dV map, right? So if you take a dI/dV map at 0 energy, you find a mode that's basically sitting right on top of this domain wall, right? So it's sort of localized to the domain wall. However, as you increase energy, so let's say you go to 0.25 millivolts, this is 250 microvolts, the size of the spatial extent of the state actually increases. And as you go to higher energy, the spatial extent increases more. And in fact, by the time you get to 1 millivolt, which is right on the edge of the flat portion of this gap, the spatial extent has spanned the sample. So this is what you expect to see. You want the surface state, you want this 1D state to actually connect, to span the gap, and that's what this 1D state is doing. It exists at all energies inside this gap, but its spatial extent increases as the energy increases. So I guess that's that. We have a lot of stuff to do. You know, like Andre said, we need to put on a magnetic field to see how these states respond to a magnetic field. There are many other things we could do because we are growing films, so we should be able to do other clever things. And, you know, I'll leave you with this. Thanks a lot for your attention.
Any more questions?
Yeah, maybe a question a little bit related maybe to the question of why design of the mass might change. So do the domain boundaries end at some point? Are they final extent?
Yeah, and if you go to the end, we often see a 0 bias peak at the end. Now, the problem with the sample is many things give you a 0 bias peak, right? What if there's an impurity at the end, right? It's actually really interesting that there's a 0 bias peak at the end, but I don't want to say that.
Do you see, so if you have an domain boundary, means that your phase shift continuously evolves towards a situation where there is no phase shift at all?
Could you repeat that again? Sorry.
So you said the image that you showed, there is a phase shift of phi between the lattice on one side and the other. And then if you have domain boundaries that end at some point, the phase shift should continuously go to 0 at this end.
So usually those ends happen near step edges.
Okay, so
Yeah, and sometimes they happen when there are two of these domain boundaries coming together like as a Y junction. So then we get an end. So you know, you can get that. So yeah, there's different geometries where you can get an end.
you have only phase shift of 0 and pi, or also
No, we don't see any others because this is a natural thing for this particular crystal, the flipping. It's a defect. So it's natural for the seleniums to just simply flip, and so we get this pi phase shift, but we don't have any others. Yeah, we have these strange 1D defects in the system which don't show this kind of feature, but there the Fourier transforms don't show anything. Andre had a question, but someone else also has a question, I think.
Yeah. Which one is the bulk gap?
So there are 3 gaps, 2 are bulk gaps, and 1 is supposedly the surface state.
So the one in the surface state,
It's in the middle.
why is it larger than one of the bulk gaps?
It has to do with the orbitals. Exactly.
At least numerically, by that time. So where's the bulk gap? The two bulk gaps.
Yeah, actually, maybe we have a few minutes. I can go back and I can show you which gaps these are. Um, yeah, so I had this table. So there are 2 hole-like bands and 1 electron-like band in this system. Oh my goodness. Okay, it's coming. Too much. Okay, there we go. All right. There we go. Okay. So alpha and beta are the 2 hole-like bands, and gamma is the electron-like band. This thing is in between these 2 gap values.
Yeah, but normally I expect the proximity gap to be smaller. If I just said one gap,
Yeah, yeah, yeah.
some surface table, you know, expect the proximity gap to be smaller.
Yeah.
So then it means that it's sometimes a larger gap, but that would happen in case they're the same.
Orbital. So these 2 are at the gamma point, and this is also at the gamma point. This surface state. That's all I can tell you. I don't know the orbital character. You know, they're slightly mixed x, y, y, z orbital characters. Yeah, sorry. So I don't know the orbital character of the surface state.
Okay, one last question, and then I should go.
The semiconductor quantifiers, they always have to challenge to discriminate or distinguish between true Majoranas and pairs of the ground states. The tricky thing is that, especially when you have impurities or irregularities, and these things can track to zero energy.
Correct. So the beauty of STM is we can rule that out. At least we can rule that out, because what we can do is we can take a nice DIDV map before we turn on the field, and we can check if there are any impurities. They'll show up with 0 bias peaks, right? And then you turn on the field, and then you see if you have a vortex on top of an impurity, then you rule that one out. You say we don't think about that one. But there are plenty of vortices which are pretty far from impurities which still show the 0 bias peaks.
You never ever see a pair of these guys coming down. I mean, it looks so clean. I mean, you never see splits.
We didn't do huge statistics on the vortex core states. There's a paper which may already be published now by Hanaguri's group, and they did extensive work on the vortex core states, including the impurity bound states. And they're able to show all kinds of things, including you should see other bound states, vortex bound states inside the gap. They see that. They're able to distinguish between the impurity states and the vortex core states. So they did a lot of statistics. And certainly it seems like they can isolate vortex cores and show that there's a true 0 bias state. The other interesting thing they see, which they don't understand, is as they increase the magnetic field, many of the vortex cores that used to show these 0 bias states don't show them anymore. The peaks get suppressed. So it's something to think about.
Okay, let's thank Vidya again.